Welcome to today's Explainer, where we're going to unpack some genuinely groundbreaking AI news from a paper slated for DAC 2026. Look, if you work in machine learning infrastructure, you already know the deal. Large language model inference costs are this massive, constant burden. Well, today we're looking at a brand new GPU inference method that directly attacks one of the most frustrating bottlenecks in that entire pipeline. By optimizing sparse matrix multiplication at roughly 50% unstructured sparsity, researchers have unlocked some seriously massive performance gains that, honestly, people previously thought were impossible. Here's our roadmap for this explainer. First, we'll cover the sparsity performance paradox. Second, a 3-layer matrix solution. Third, hybrid pipeline execution. Fourth, shattering previous benchmark ceilings. And finally, deploying the SpInfer kernel. All right, section 1, the sparsity performance paradox. So we're kicking things off with a massive mythbuster that constantly plagues ML engineers trying to save a buck on compute. It's the ultimate sparsity paradox. You do the completely logical thing, right? You prune a model to save money and reduce compute. You go ahead and delete half the weights. But instead of speeding up, your inference actually bogs down. It literally runs slower than if you had just left the model at its full, massive size. Why on earth does doing less math take more time? To get this, we've got to talk about unstructured sparsity. This is when you remove individual model weights, literally just setting them to 0, without following any kind of rigid geometric pattern, like that popular 2-4 structured sparsity you might see supported on NVIDIA hardware. Now, to preserve your model's accuracy and keep the output quality from totally collapsing, practitioners typically cap this unstructured sparsity right at that 50% sweet spot. But as you'll see, this specific threshold creates a massive headache for modern GPU hardware. And this breaks down exactly why. Think of a dense matrix multiplication, or dense matmul, as reading a solid block of text on a page. The GPU reads it smoothly, sequentially, and it entirely avoids any structural overhead. But 50% unstructured sparsity? That's like reading a book where every other word is just randomly missing. It creates these highly irregular access patterns. Your GPU is constantly pausing, trying to figure out where the next non-zero value actually is. This sparse index decoding eats up precious cycles, causes memory fragmentation, and ultimately just constantly stalls your high bandwidth memory, your HBM. The hardware ends up just waiting around rather than calculating. And that is exactly why the dense matmul, even with double the actual math, easily wins the race. Moving on to section 2, a 3-layer matrix solution. So how do we actually fix this dead zone where sparse kernels just can't beat their dense counterparts? Well, the researchers unveiled a truly brilliant 3-layer matrix storage format. Instead of just forcing a standard matrix through the hardware, they systematically divide and conquer the memory bandwidth and decoding bottlenecks. The format splits the weight matrices into 3 stacked layers: a sparse TC layer to map non-zero weights directly to sparse tensor cores, a slot-filling layer for compression, and finally a residual layer to guarantee accuracy. Now, the real secret sauce of this format is absolutely in the slot-filling layer. By using something they call parallel differential distance encoding, it heavily compresses the overall weight layout. But here's the kicker. This specific structure enables ultra-low-cost on-chip decoding. It basically slashes that index fetch penalty we were just talking about, the exact latency bottleneck that normally completely kills sparse kernel performance. It organizes the sparse data so the hardware can actually digest it without choking. And then, crucially, we have the residual layer. Look, whenever you mess around with matrix compression, you always risk losing numerical precision. But the residual layer stores just the minimal correction data required to maintain exact computation. This guarantees exact numerical parity with your original dense model. For a developer, this is a total game changer. It means you absolutely do not need to adjust your tolerance thresholds or go through the painful, expensive process of retraining your models just to accommodate the new format. It just works exactly the same way your dense model did. Section 3. Hybrid pipeline execution. Having a smart data format is really only half the battle. You also have to execute it efficiently. The custom sparse matrix multiplication, or SpInfer, kernel built on this format runs a hybrid execution pipeline. It intelligently schedules the workload across both the specialized sparse tensor cores and your standard CUDA cores. And by doing this, it overlaps the on-chip decoding and computation with the memory fetches. So while one part of the GPU is busy fetching data, another part is actively calculating. It completely hides those annoying latency stalls that previously ruined sparse workloads. The crucial takeaway here is that by successfully hiding this latency, this research represents the very first reported case where unstructured sparse matmul actually outperforms dense matmul on modern GPUs equipped with high bandwidth memory. They've officially broken the 50% sparsity curse.
Which brings us to Section 4, shattering previous benchmark ceilings.
Let's look at the hard proof and the real-world AI news impact of these architectural breakthroughs, because the benchmarking data establishes some very clear, brand new performance boundaries. At the kernel level, this new method achieves an incredible 1.64x speedup over SpInfer. Keep in mind, SpInfer was a best paper winner at Eurosys 2025. Beating it by over 60% at the kernel level is a generational leap in optimization for sparse matrix multiplication at the specific 50% unstructured level. But kernel speed doesn't mean much if it doesn't translate to actual application speed, right? Well, for end-to-end large language model inference, this method delivers a 1.41x speedup over FlashLLM, which was just presented at VLDB 2024. These aren't just theoretical, on-paper gains. They stem directly from that memory compute overlap and the slot-filling decoding strategy we discussed, directly attacking that index fetch bottleneck. And the researchers didn't just test this on little toy models either. As you can see here, they rigorously tested across heavyweights like OPT30B and OPT66B. They used NVIDIA H100 SXM5 GPUs and ran batch sizes of 16 and 32. And they proved consistent dominance across 50, 60, and 70% sparsity levels, consistently beating established baselines like SpInfer, FlashLLM, Spartia, and Sputnik. This robust testing proves it's a highly stable, high-performance solution. Let's wrap up with Section 5, deploying the SpInM kernel. I know exactly what you're thinking. Okay, sounds amazing in a paper, but how quickly can I actually get this running in my own infra? The implementation path is surprisingly straightforward, but there are some strict prerequisites. You absolutely need modern high-bandwidth memory hardware. The speedups require an NVIDIA SM-Score 90A GPU, so we're talking an H100 or an H800. Older GDDR-based architectures simply won't sustain the memory bandwidth needed to hide that decoding latency. You'll also need CMake 3.20 or higher and CUDA Toolkit 12.6. Your target model needs to be sitting at that roughly 50% unstructured sparsity mark. Models pruned way beyond this, or those using strict structured patterns, won't really benefit from this layout. Finally, converting your dense weights to the 3-layer format does require a one-time pre-processing step. But honestly, because the inference time savings compound across literally every single token you generate, that upfront processing is a completely negligible cost for production. And best of all, the researchers have open-sourced the whole thing. The source code is publicly available right now at the CUDAC repository on GitHub. You can take the provided SpInM kernels and use them as drop-in replacements for your inference engine's existing matrix multiplication calls. You could literally be benchmarking this against your current backend today using your own identical model weights. This really brilliantly illustrates the core takeaway from this entire explainer. The researchers state evaluations show that our work is the first to outperform dense matrix multiplication on modern GPUs equipped with high bandwidth memory. The supposed 50% dead zone for unstructured sparsity wasn't some hard limit of physics. It was simply a software-hardware mismatch just waiting to be solved by some clever engineering. Which leaves us with a really critical question to consider. Knowing that you can now prune unstructured weights at the 50% mark without sacrificing accuracy, and now, without sacrificing hardware speed, how will this change your threshold for model pruning? How will you redesign your own model deployment strategies going forward, now that this massive bottleneck has been completely shattered? Thank you so much for joining me on this explainer, and I highly recommend heading over to that GitHub repo to see this architecture in action for yourself.